Okay, welcome, folks. If you can hear my voice, please put something in the chat and let's start. So last time we implement ray sphere intersection. So if we run this program, we can see this little sphere on the screen with the normal vector as our final color. And yeah, that's basically it. We implement like vector class, ray class, and sphere class. So I think today the first priority is to support multiple primitives. In the book, they have this thing called hitable list. That is basically what we do is multiple primitives. Is when we hit, we loop through all of them, and we do hit test of all of them, and then we get the closest. This function will be a bit tricky because it's really imperative. So imperative loop is hard to kind of refactor into functional way to do stuff. Let's start. So let's create a C module. What is this? So sorry, I practiced yesterday and it seems it's already here. That shouldn't happen. What? Okay, anyway, let's just talk about this. So basically we have a thing, and the type is a list of sphere because we don't have a polymorphic geometries yet. Once we support second primitives, we need that, and we have this add function that just adds stuff to the thing. And this function is this loop. So it looks quite different. But the thing is, for this loop, what we basically do is find the minimum of the closest hit and then return. So this is finding the minimum, but first we need to do all the hit. So like we do all the hits with a map function, intersection test, and then we filter out all the sphere that don't hit with this monadic bind, because if it hits, then if it don't hit, then we don't need to kind of continue doing stuff, and then we just do this main element function that compare to the hit record, and choose the one which is smaller. So I guess the tricky part of this function is bind, because not everyone is familiar with monadic programming, but the idea of this line is basically we have a list of hit record option, because some of sphere may may not intersect at all, and this line just filter out those and generate a new list. We cannot use filter. We cannot use filter for this line because if we only filter the filter list, then what we get is still a list of optional, but we want a list of hit record, not optional. So that's basically it. That doesn't change anything because we haven't used this yet. And now in here, we need to create our thing. Let's create our thing outside. So in the book, they have one small sphere and another gigantic sphere. So yeah, it's here. So you can see this sphere radius is 100, but it's placed like a bit away from us, so we can actually see it as kind of the ground of our thing. And with those two in place, we can have our thing. Because we haven't. Yeah. For some reason, the Merlin, that is the OCaml kind of the auto completion tool, I need to build first to make it work. So we added the two sphere to the thing. Notice this add function, so it takes a sphere and a thing and returns a new thing. So it doesn't mutate the thing because thing is an immutable list. Later, when we add accelerating data structures, this whole module needs to be kind of revoked, and we probably need some kind of builder pattern because it is hard to have. Well, it is hard to have like this kind of add function, but instead we may want to add all the geometries to a builder, and then the builder will create the acceleration data structure at once. Because we need like all the global scene information to make the acceleration data structure. Hey. Oh, sorry. I don't know if I have the test for the scene. Oh, I got that deleted. I guess I got that deleted. That's good. Let's see what is in here that shouldn't. This, and this. Let's quickly do some tests for the scene. We need two spheres. We'll just put it a little bit away. First, let's just copy and paste this one. That should be exactly the same. No, sorry. Yeah. But if we have a ray at opposite direction, then it should hit the second object, not the first. So let's change what we did for here is -3. In this case, 5 to 3 is 2, minus the radius 0.5, so it's 1.5. And the position is -3.5. Normal should be in the negative direction. Looks good. Let's add the final miss case. Because we haven't changed this. Those tests looks really trivial now, like just look at this implementation, it's so simple, what can be wrong? But it's really good for regression tests, so later we will refactor this whole module into using acceleration data structures. And when we do a refactor, those tests should still pass, so that's the point. Okay, so the test is good, and now we need to use our thing here. No longer use sphere. Now we have another sphere at the ground that shows the same image of the book. So before we continue, last time we talked about I want to have some monetic extension for the optional. I look at the OCaml standard library, I cannot find anything, so let's add our own. Just for convenience. Don't even know we need base or not. Let or else will be a function that take another function that map from nothing to the not nothing, actually it's a unit to the value of some polymorphic option. This is okay. And also a real option. The reason we need a function instead of just like some like option as this parameter is we want this calculation to happen lazily, not eagerly, because we don't want to do this calculation if we don't need to. Yes, we don't even need this. If it's null, then we run this function. If it's sum, then we do nothing. That's the idea, is like error handling. That's why this is called all else. The idea is for types like option that the happy path is a monad where we have bind, which is this function that maps the value, and if it doesn't have a value, it's just do nothing. For this all else, it's exactly opposite. So we treat the non-value case as a monad, and the bind, this is a bind function of non-value case, where if we don't have a function, well, we don't have a value, then we apply this function. If we do have a value, then we do nothing. Well, what's wrong with this syntax? I used the variable var. Oh. Wait, what? Okay, should be good. Let's do some test for that. Or else no. We haven't exported that. We have a function that takes a unit and just return someone. So that test means if this is none, which it is, then we get some 1. So it should be some 1. That's okay. If we use if this option already have a value, then it should just preserve that value and ignore that function. That looks fine. So now in our sphere, instead of doing this pattern matching, we can do or else. Test still passes. And the image looks fine. So I hope this code is a little bit cleaner than the previous one when we have this pattern matching and there's some redundant logic. Okay, let's continue. Anti-aliasing. So this is the part. This chapter is a part where this book start to diverge from the other ray tracing algorithm we talk about. So this book talk about an algorithm called path tracing, which is the idea that we have a lot of rays per pixel, a lot of samples basically, and then all those samples, when they hit some surface, they reflect all refract according to some distribution, and then we accumulate the contribution of all of those samples together. I'm not saying like sum those contributions because we may have a weighted sum, so I will just accumulate those distributions and then just get a result. If you look at this book, it will use like 100 sample per pixel. If you just want to do anti-aliasing, it's totally unnecessary. But for the path tracing algorithm, more sample per pixel means better image quality. So that's what we will pursue. To use this anti-aliasing, first the book do some refactoring of put camera into its own class. So in the OCaml world, class means a module, so let's do a module instead. And Just copy paste and this line here, those 4 lines. So those values are hard-coded. Later, when we want to do cameras with different values, we need to revisit this here and to change so camera can have like configurable settings. I don't even need to just. This is how to get line from the camera. Get array, sorry, not get line. And with this camera module in place, we can delete those 4 lines. And in here, let r equal to camera get array. Should be the same. The next step is to actually have multiple samples. So like in here we like do 100 samples and each of them add some randomness jittering. So like if we have a pixel box like this, currently we are just always sample this point, but what we want is sample like this point, this point, this point, this point, etc. randomly. There are better way to like do this than uniform distribution, but for simplicity, we now will just do a uniform distribution. First, let's add more samples. As a book, we will say sample per pixel is 100. Then in here, we need to do sequence. Like get all those samples and fold the samples. Well, fold the result, I should say. Like the result is calculating the color, and then we just like add all the colors and then average them. We are not doing anything fancy about sampling yet. The index doesn't matter. But color is an accumulator. What's wrong with here? Use variable color ACC. Yeah. So a lot of functions in base library, which is the OCaml library, we use this kind of named argument. So that will also be what we will do for like our previous option extension function. Equal to color ACC divided by to float sample per pixel. We forgot init for the fold. Our initial color should just be black, and then we add contribution. That's probably a good time to add another helper. So, I don't know if you can see it, but from my perspective, I can clearly see previous when we execute OCaml PT, it's just kind of exits almost instantaneously, but now it have a little bit of lag because we are doing 100 times more jobs. The image should looks the same because we haven't done any kind of randomness yet. And you can see the alias is still there. It's like those kind of sharp edges because all our samples are the same. So now is the time to add some randomness. In the book, they just add a random double for each and I of j coordinate to calculate the pixel coordinate inside here. So currently our ij is at here. If we add some number, then we calculate, we get some any point from here to here. And since our random number are uniform distributed, we get a uniform distributed in 2D chord point. So the base library contains this random module. I'm not happy with this random module because all those basic functions mutate global random states. So what's wrong with global mutable states? The problem is our path tracer or ray tracer, all of those algorithms are like embarrassing parallel algorithm. So once we finish this book, finish all the content from this book, and it also have 2 sequels. After all of those, the first thing I will do is to parallelize this program. And if we share some global mutable state, then the performance will be horrible. When all those like random number happen, and in this path tracer, like using random number generator happens a lot, and that kind of thing also happened in my C++ implementation I did 2 years ago. And in that thing, I use thread local random number generator instead. But in the C++ standard library, random, not this. This is you should never use the rand from the C standard library for anything. In the C standard library, the random number generators are classes, and you can create those random generators in any way you want. You can like create it inside a function and it's a local random number generator, or you can make it a static thread local. For here, this is base random is basically a singleton, and there are no way we can kind of avoid these multiple global random states. There is some advanced function here that we can have a state and set states, but then I have a feeling that this set state function will still be a bottleneck. So let's see how it goes. Currently, I will just use this. Later, when we parallelize this code, I will refactor and do some performance comparison from this random to like whatever random we will use at that time. Currently, I will just use this for simplicity. Yeah. So this random.float function returns a random floating point number from 0 to the upper bound. So it's like from 0 to upper bound. That's exactly what we want. Now all the jittering are gone. Should be. Not jittering, the aliasing should gone. It looks smooth, but we are doing 100 times more work. So what's the point? The point comes next when we start doing with the diffuse material. But before that, we also need to do some quick clamp here. So this clamp will return all arrow type if the max is less than min, it will like return an error. But since in our use case it's like min and max are not variables, they are kind of, we fix them. It's a hard-coded value, so we will just use this, let it throw exception. It doesn't matter because it will never throw anyway. So basically the idea is in our case, like this thing will throw is a bug. So we don't need to use control flow to handle this case. I'm not saying like exception is the best way to handle this kind of functions. Like this kind of functions should never fail anyway, so it should be like an assert or like Rust panic, something like that, because we don't need to catch them anyway. And for something catchable, we should just use control flow. I don't like exceptions. So yeah. So basically, later if we have some lighting that is too bright, we want to make sure it's like adhere to this 0 to 1 range. Otherwise, we will have an integer that is above 255, and then I don't even know what will happen for our ppm file format, but I guess the ppm reader will be really confused. So let's deal with diffuse materials. The idea of diffuse material is that we have a surface, we have something, some like a ray comes through and intersect. Whatever the angle is, it doesn't matter. And we will just get this kind of reflection uniformly distributed across a sphere, a hemisphere I should say, because we will not have rays like go this way. It's not transparent. That's probably the dumbest material we will have, and we will not use this implementation. Instead, we will use this. So the initial version of the book have this implementation, but then there are some comments about this implementation is not really kind of represent the true Lambertian material. True Lambertian material is like totally diffused material, which is what we are working on. So we'll use this to get a random unit vector. We need to make this function a thunk again, just like in our or else, because this thing has side effect. So we want it to run every time, not just the time, just like have a fixed number for it. So there's another function called random.floatRange, which is a little bit from random.float. This kind of hard-coded the lower bound to 0, and this function is more flexible in that way. We probably need to open float. If we open float, then in this float module, it defines it overrides those arithmetic functions, so we can directly use it. But I cannot like override those functions, those operators in the same way like in our vector, because in our vector we have like we still use this scalar operator, so we don't want them to collide. And in some cases, we want to mix integer and floating point stuff together. In that case, then the only choice is to use those long operators. But if we only care about floating points, like in this small function, then it will be a little easier to just open the float module and Yeah, this function. So this function, we get a unit vector from it. I will not walk through this function. It's pretty trivial. A hint is it's spherical coordinates, and yeah, basically you can like reason this function yourself. It's pretty trivial. And then in our recolor, instead of a fixed recolor, we well, instead of using the normal, we like calculate the target ray, target's position, I should say. Like where our ray will be at. Call it hit record. Just call it. We cannot use rec. Yeah, we cannot use rec because rec is a keyword in OCaml. And now we just hard coded that our Lambertian material will absorb like 0.5% of light, and that's why we have this multiplication here. But remember, we need to do this, not now we just have a hard-coded thing, we don't pass it in, so this is fine. Now look at this, beautiful. So we have our first image that look like some real scenario, not just computer graphics weird experiment. So the book had a depth limit, so let's also add that. First have a helper function. Also take array. We need to take array because array changes. In here, let's add another max depth is 50, so we restrict our recursive depths in, and then we say if depth is greater than 50, then it's black. else we do all the dance we did before, but in here we don't call recolor, we call helper. With the depth is current depth plus 1. The depth starts from 0. Nothing should change. So this function is not too recursive because we call helper at here instead of at the end. Let's leave it for now because later we will refactor this material logic into its own place. So let's leave it for now. Later we will definitely refactor this function into tail recursive. And it looks good. The next step is gamma correction. So color is what we call color is not just 3 value, but actually color spaces, and there are different color spaces. So there are linear space that's good for approximate lightning calculation, which it is still just a approximation. If you want to go really hardcore, you need kind of some like distribution function of light waves, and then you can just, if you want to know more, you can look at the book called Physically Based Rendering. It have a chapter about those like radiance and color science stuff, radiometry and color science stuff. And for now, I will think linear color is good enough for the color calculation, for the lightning calculation in our ray tracing. However, linear RGB is what is not displayed on the screen or like stored in those kind of images. What used in the images and also on the screen are called in the gamma space, not in the linear space. And the gamma space is usually like exponential to like of this color value to some gamma. Usually the gamma value is 2.2, not 2.0. The book just using approximation, so we can use square root. But I will use 2.2. Let 2 gamma space. You can search gamma correction for more information about this. I always forget about that. This syntax makes this like this just for better syntax highlighting. This is correct. equation. And power, yeah, I think that's right. Notice we use the same vector type for vectors, for points, for color, for everything. As I said before, if you want to get like really serious, then probably it's a good idea to separate those types. But the book just uses vector type for everything, and also I'm lazy. I don't want to write all those types with similar functionalities. But if you want like stronger types, then it's a good idea to have separate types for color. And also, if you're interested, you can read if and vector types, like how vector and point types should be designed. So gamma space is not used yet. In here, we don't need to do that. Just fine. Just we do this as the final step. Aha. So our image looks a lot brighter in the gamma space than the linear space. So the idea why the monitor had the trouble of storing color in like gamma space is because for human eyes we are more adapted to darkness. So like in darkness we can see like smaller differences, and when the thing is bright we are not that easy to see the differences. So by using the gamma space, basically with the same amount of byte, we can store more information. But as we said before, those kind of curved space is not good for doing any kind of lightning calculation, because it definitely don't follow the vector superposition principle, stuff like that. And if we mindlessly add them together, we just get incorrect image like what we get before. Even though in computer graphics, a lot of time it's not obvious if your image is correct or not. Another thing we want to address is to add the minimum amount of t to some value that is greater than 0. I don't think we care about Tmax anymore. We check Tmax globally in our scene module, not in here. Yeah, it does better. The reason we need this kind of epsilon value of t minimum, not just directly using 0, is because floating point errors. So let's say we have a sphere like this. We have a ray intersect at this point, but due to some floating point error, we actually get this point instead. And then we calculate the reflecting ray, and hey, we intersect at here again. So this is wrong, and we just get we just like, we should go this way, but we like hit here and the algorithm think we kind of hit a surface again. So this problem is not that obvious in path tracing because we have a lot of samples, but if we have one sample per pixel and using shadow rays like in the vanilla weighted retracing algorithm, we can get some really horrible artifact called self-shadowing. Come on, Wikipedia is never helpful. Yeah, something looked like this. So it's just completely garbage because of this floating points precision problem. That's why we need this little bit of epsilon value to make stuff work smoothly. Okay, thank you for watching. That's all for today. So we have a pretty beautiful image here. Let me do a quick So next time we will actually have polymorphic materials because we need to handle more than one. We will have metals and electric material, and that's basically the book. So next time we will finish the book. We'll also have some additional stuff like this camera become like parameterized and I think motion blur. Yeah, that's it. Not motion blur, depth of field. And I think next time we can finish this book and then we can work on the sequel of this book. And I think in the sequel of the book, we add accelerating data structures. I forget what else is in there. Okay, thank you for watching this episode of live coding ray tracing in a weekend in OCaml. I know this is shorter than the last episode because I'm hungry and I haven't eaten lunch yet. So see you next time.